Hello students, in this video we'll solve a Lower Michigan math competition problem that involves defining what the composition of a number is. We say that a positive integer n has a composition has composition, not in, has composition of all possible ordered sums. And order is important. Ordered sums that add to n. And they have to be of positive integers as well, of positive integers. So let's do an example of this. An example of this, the classic example is just what 4 would be. So if I give you the positive integer 4 can be written as 4. It can be written as 3 plus 1 or 1 plus 3. Now I'm saying they're ordered because now 3 then 1, right? So they're ordered. Then a what? You could do a 2 and a 2. You could do a 2 and a 1 and a 1. You could do a 1 and a 2 and a 1. You could do a 1 and a 1 and a 2. Or you could do a 1 and a 1 and a 1 and a 1, like that. Those are the orderings. That's the composition of 4, right? Okay, so the composition of 4, there's a whole bunch of terms. Now we're going to look at special subclasses of compositions. Let's let an be the number of compositions of n with no 2 ones in a row. And let's let bn be the number of compositions with the maximum number being no more than 3. Less than or equal to 3. We're going to prove the following. Prove that b of 2025 is equal to a of 2025 plus a of 2026 over 2. That's our goal, okay? Again, the year pops up to first is the red herring, right? Total red herring. So now how we go about proving this? So we're going to prove they satisfy the same recursion, right? So what can I claim? So we claim both an and bn satisfy the following recursion. Bn is equal to bn minus 1 plus bn minus 2 plus bn minus 3, right? How do I see that? Okay, I see that because what can I do? I can simply just remove the what. This is true for, clearly this is true for b. This is true for bn by removing the first term from the sequence b. Of the sequence. Okay, excellent, because that will put you either into a situation where you have a 1, a 2, or a 3, right? Because that's all you have over there. And of course, then you split that, the 3 can be split down 3 levels, the 2 can be split down 2 levels, the 1 can be split down 1 level. That's it, right? So if it was a 1, you get those number of terms left over. If it was a 2, you get a 2 or then a what? And then 1 and 1 potentially, right? So that we went on 2 levels, and then the 3 we went on 1 and 1, 3 levels, right? So if that satisfies that recursion, how do we get this same situation for the ans, right? So with an, what you could do is the following. So an, so let's let an be the number, the set of compositions with no 2 ones in a row. Okay? Then of course, how can you decompose a? This can be decomposed in the following way. You can have a 2 and then a what? Then you can have a 2 plus a series of n minus 2 terms with no double ones. Or you can have a 1 and a 2 plus n minus 3 terms with no 1, 1. Then you could have a k plus n minus k terms with no 1, 1. And then you can have a what? And then you can have a 1 plus k for k bigger than or equal to 3, right? K bigger than or equal to 3. Then plus n minus k minus 1 terms with no 1. Okay? So of course, these terms map into an minus 2, these terms map into an minus 3, and these terms by decreasing k by 1, it's meaning the next level, will go to what? An minus 1. So this implies, therefore, that an is isomorphic, is in 1-to-1 copy to what? To an minus 1 union an minus 2 union an minus 3. And that says that an is equal to an minus 1 plus an minus 2 plus an minus 3, like that. So they satisfy the same recursion relationship, right? And so in particular, this says that the average, this says that we can claim that bn is equal to an plus 1 over 2. Now, how can we claim that? If it's true for both of these things, they satisfy the same recursion, right? They both satisfy this recursion over here. So if I can prove it starts true, it will remain true, right? So we got to test the first couple of values. What are the values? So the first value, b1. So b1 is clearly just 1. b2 is clearly going to be what? b2, let's think. We can have two things in b2, and then b3 is going to be 4, right? a1 is going to be 1. a2 is going to be 1. a3 is going to be what? Well, now there's something more there. There's going to be what? There's going to be 3 of those things over there. Right, because what can we do for 3? For 3 of those things, we could have 3 itself, 2 plus 1 or 1 plus 2. That's it. So there's 3 of those. And then what's the hard one? a4. Let's count what a4 is going to be. a4 should be 6, right? So, oh, we have it up here. Look at that. That's nice. So let's see. We have a 1, 2, 3, 4. Can't have that one. 5. I'm missing one over here. 6. No, 5. It's 5. Yeah, 5. a4 is equal to 5. It has to be 5. Not 6. Good. Okay. Why so? Because now what is b1? So b1 is 1 plus 1 over 2. Good. What's b2? b2 is 2. That's 1 plus 3 over 2. Great. What's b3? So I know that b1 is a1 plus a2 over 2. b2 is a2 plus a3 over 2. And b3 is a3 plus a4 over 2. So both of these recursive sequences over here satisfy the same recursion relationship, and they start off with the same 3 values. We're done, because now this is just a trivial consequence of the fact that those two sequences have to be identically equal to each other, right? So by carefully counting and ensuring they satisfy the same recursion relationship over here, what we saw from this structure, as I said, I looked at this problem and I said, oh, look, the 2025 is a red herring, right? It's a very large number, right? That corresponds to the year, right? And if this is going to be true for 2025, it should be true for any number, any sufficiently large number. This is not a function of the fact that there's some sort of deep intrinsic meaning or number theoretic property of 2025, which helps with this. We'll see that in further videos. But it's an example of saying that I'm just going to plug in any parameter I want because both these things satisfy the same recursion relationship. Thank you very much.